Have you gone full circle yet? Yeah, there you go. Oh no, it's not working, eh? Okay. Hey, is my mic working now? Okay. Okay, good. Okay. For what it's worth, I love hearing your guys banter. It's like my favorite part of the day. You guys are the best. Okay, so yeah, we're gonna just jump on into it. Yeah, so we've got a few different tests to sort of wrap our heads around in this chapter, and I've kind of just spent the past couple hours sort of going through the textbook and sort of going through the different chapters, and it's a little bit messy. So what I thought I'd do today is just sort of make a list, and I know that I did this a little bit yesterday. Like I think at the beginning of yesterday's class I had like a summary, but it wasn't actually complete. There's a few things on here that are incomplete. So I thought that I would just try to make a complete list of like all the tests that are in this entire chapter, not just each section, but the whole chapter. So chapter 11, and so I've kind of summarized it, and there's only a couple of things that we haven't covered on this yet, and they're in 11.5, and then I think, what is it, 11.6, that is on Taylor's inequality. So we're gonna save that one for later. I'm just double checking. Is that what 11.6 is? I'm pretty sure 11.6 is Taylor's. Yeah. So 11.6 is on Taylor's inequality. We're going to leave that. We're not going to talk about that today. That's like a whole section in and of itself. So we'll spend a whole day talking about Taylor's inequality. In the meantime, we're going to talk about sort of like what's our strategy? Like what is this chapter all about? Like what are we trying to do here? And okay, because it kind of seems like the chapter started off by talking about approximations, right? Like we started off talking about approximating a function using, like, by taking several derivatives at 0 or the derivative at a specific point, right? Like those are the Maclaurin polynomial or the Taylor polynomial at a certain point, right? We started off with that, and then all of a sudden we started talking about these infinite series and that sort of thing. So, I mean, the idea here is that we're going to be given a function, right? We like our final goal should be that we should be able to be given any function, not just a polynomial function, but just any function like an exponential function or a trigonometric function or something like that, and we should be able to approximate it with a polynomial. And if we keep approximating it, like if we keep, taking that Taylor series to infinity, like if we take an infinite number of derivatives, like is there some kind of pattern? And if so, like how sure can we be that, for one, the Taylor series will converge? And that's really what like all of this is about, is like convergence or divergence, right? Like does our like if we're given some kind of infinite sum, does it converge or diverge? And if there's an x in there, so if it's a function of x, like for which values of x does it converge? Converge. Okay, and then that's the radius of convergence. Okay, so that's kind of the big picture of what we're doing here, is that that we're kind of doing two things at once. On the one hand, we're approximating functions, and on the other hand, we are looking at infinite series and seeing when they converge or diverge. And then there's the intersection of the two, where we take a function, find its Taylor series, and see if that converges and diverges, and if it does converge, then for which values of x does it converge? Maybe all values of x, as we saw on the exit slip yesterday. If you looked at the last page in the book and looked at the solutions, you would see that the radius of convergence is infinity, so it converges for all values of x. So that's that, and then there's this little thing over here, Taylor's inequality, which we'll get to. I'm really hoping we can finish chapter 11 by the end of the week, but we'll see. It would be really great, because this is the last chapter, and then if we did finish chapter 11, then we'd be done, and we could just start doing some reviews. So I'm hoping we can do Taylor's inequality by Friday, but like I said, we'll just sort of have to play it by ear. Anyway, with Taylor's inequality, this is about like how accurate is our Taylor series approximation. That's really what Taylor's inequality is all about. Is our Taylor series actually a good approximation to our function? And we've seen so far that it can be pretty good. Like it looks pretty good so far. But yeah, that's really what we're doing. This is what this is all about. So we've looked already at the nth term test. So the nth term test tells us, okay, if the terms that we're adding up, if they don't end up, getting close to 0, then our sum diverges, right? If the terms do tend towards 0, well, that means nothing, right? Well, it doesn't mean nothing, but it means that we have to keep looking, right? Then we have the alternating series test, and somehow I think I may have skipped that, so I want to just quickly cover that, because I didn't see it on our list from yesterday. I didn't talk about the alternating series test, and I think that's because that is in 11.5 for some reason. Like I said, this chapter of the textbook is kind of all over the place. It's hard to sort of keep track of all of the different tests and everything. So I'm trying to sort of put them all together. And I think there is a page in your textbook that does sort of consolidate everything. Let me see if I can find. Yeah. Page 510 is a good. Just take note. You don't have to look at it right now, but take a look at page 510. It's a good page. It summarizes a lot of information. There's a few other pages that sort of consolidate a lot of what we've learned. Yeah, page 500 is a good one too. Page 500, that's a good page. Kind of tells you a little bit about the radius of convergence of famous functions. And I think those are the two pages that really stood out to me as being good pages to take note of. And I'll just put page 492. It's a good summary of 11.2, page 492. So these are three great pages in your textbook. I would spend a little bit of time on them. I'm not trying to say that like all the other pages are awful and bad, and I'm also not trying to say that if you read those pages then you don't have to read anything else in the book, but those are good pages to take note of, and I'd recommend that you look at them today. Okay, so alternating series test. I'm going to go over that today. Geometric series we looked at, right? We should be able to recognize when a series is geometric. The ratio test, we also looked at that. If you look at the ratio between terms and take a look at where that ratio is going as we get further and further into the series, like what are the ratio between consecutive terms? If that tends towards 0, then, it's not if it tends towards 0, is that if that ratio, like if the limit of the ratio is less than 1, then we're good. And with the endpoints, I told you I'd talk a little bit about the endpoints. Well, with the endpoints, there's 3 things we can do. We can take a look at the nth term test again, right? That can be a good way to look at the the endpoints, because that can tell you if it diverges, right? But we've already looked at the nth term test. There's the p-series test, which we're going to talk about in a minute, and there is the integral test, which we will talk about in a minute. And I believe the p-series test and the integral test are parts of 11.5. But like I said, it's been hard to keep track of all the different tests. Okay, so alternating series test is 11.5. There's stuff on absolute convergence, which we'll talk about tomorrow. Yeah, there's the P-series test. Yeah, I can't keep track of which chapter has which test. There's, like I said, they're all over the place. Anyways, but I haven't spoken about them yet, so I'll talk about them today. So we'll talk about the P-series test and the integral test. So those are the three things we're going to focus on today, is the alternating series test. We'll do the P-series test and the integral test. And those are the three tests that we're going to look at today. Are there any questions before we jump into it? I can hear someone's microphone. I don't know if that's anything. No, we're good? Okay, fantastic. Oh, look at that. I just looked at the cameras. It looks like you dyed your hair. That's awesome. Good job. Okay, great. Yeah, I know that it can be uncomfortable putting yourself in front of a camera, but if you want to join, there's a couple people who've been kind enough to share their face with me. I feel kind of, I'm not gonna lie, I feel a little lonely. Just there's Nick. Hey, buddy. Awesome. Okay, so yeah, if you want to join in, yeah, feel free. It'd be great to see your face. Anyway, we're gonna look at the alternating series test first. I think that's the most straightforward one. Then we'll do P-series. Then we'll do integral test. Okay. So, oh, there he is. Hey, buddy. Okay, this is awesome. Okay, so alternating series test. Let's do that. Alternating series test. Okay, so the alternating series test talks about things that kind of look like the alternating harmonic series, right? Because we looked at let's recall the harmonic series. Okay, remember that was this one over here, n equals 1 to infinity of 1 over n, right? So that's the harmonic series, and we noticed that this diverges. Okay, so this function diverges, or not function, this sum diverges. The alternating harmonic series, I can't write today, harmonic series, that is this one, sum n equals 1 to infinity of negative 1 to the n over n, and this converges. It converges. Okay, so the difference is, well, the harmonic series is this one. We've got 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus, and so on, right? Pretty straightforward. And this one diverges. The other one would be negative 1 over 1 plus 1 over 2 minus 1 over 3 plus 1 over 4 minus 1 over 5. So basically all the odd terms, the terms with an odd denominator, all the ones with an odd denominator have a minus sign in front of it. And the terms with an even denominator, they have a positive in front of them. So that should tell us something about, like, something is funny going on here, because these are almost the same series, except one of them has negatives and it's going back and forth and back and forth. The other one doesn't. So let's talk about the alternating series test. The alternating series test says, so I'm just going to write alternating series test, that says the following. Okay, I've got it right here. I just want to make sure that I'm getting it right. Okay, so let's say that we have the series n equals 1 to infinity, and I have to turn my, hey Siri.
Okay, I found this on the web for n equals 1 to infinity. Check it out.
Thank you. Okay. Okay, let's say that we have this series. It's an infinite series going from 1 to infinity. I think that this was from 11.3. I've lost track of where these tests are. I don't believe that I've shown this to you, but it may be in the book. So I think that it may have been a test that maybe I skipped in the book, but I'm telling you now. So, yeah. Have I shown this to you? I don't think I have. Yeah, I don't think I have. Okay, so this is the alternating series test. So let's say that I've got this infinite sum, and then the idea here is that an, we should be able to write it. So if an is equal to negative 1 to the power of n times b of n for some b sub n. So basically, if the terms are going back and forth, that's really all it's saying. So this part right here, the negative 1 to the n, is saying a to the n goes from positive to negative between terms. So like the alternating series test, right? So if it goes back and forth from positive to negative. So if we can write an such as this, and if the limit as b, or sorry, not b, as if the limit as n goes to infinity of bn equals 0, bn equals 0, and one more, for all n, bn is greater or equal to bn plus 1, i.e. the sequence bn is decreasing. So each term is getting smaller and smaller and smaller as it gets closer and closer to 0. Keep in mind, these two things are not necessarily equal. So these are not equivalent. Right? Just because the terms are getting smaller and smaller and smaller does not mean that you're getting closer and closer to 0, right? Like you could start at 2 and get closer and closer and closer to 1, right? Did my video just turn off? Oh, no, it didn't. So yeah, you could start off at 2 and get closer and closer and closer and closer to 1. You'd be decreasing each time, but you wouldn't be getting to 0. So these two things are not necessarily the same. So these are not equivalent. So if you have these three things satisfied, if the terms are alternating, so if we have an alternating sequence, and we have that the limit of that sequence tends towards 0, and if the sequence is decreasing, then the sum of n equals 1 to infinity of an converges. Okay, so that's the alternating series test. Okay. Not necessarily, because you could have a sequence that gets bigger and then gets smaller. You could also have a sequence that, like you could have a sequence that, okay, let's say that this is like, this represents n, and this represents an, okay? So you could have a sequence that kind of goes like this. Do you know what I mean? Like you're getting closer and closer towards n, but you know, this term right over here is smaller than this term, so they're not equivalent. So you do need it to be, it doesn't have to be strictly decreasing. Like you could have something like this where it, it goes like this, where you're getting closer and closer to, like, this would work. So it's not so much that like this value of an is the same as this value of an, but eventually you are getting smaller. So these two are related, and so that they're smaller. So the further and further to the right you go, like the bigger that n gets, you must get at most your old an. So you have to be getting smaller or at least staying the same, but you can't be getting bigger. Okay, so that is the alternating series test. So that's the alternating series test, and we can do some examples in a minute. What time do we? Okay, so we've got 15 minutes left. So that's the alternating series test. Okay, so I'm gonna give us a check for that one. We've done geometric, ratio, when we test the endpoints. Okay, now we're gonna look at the P series test. P series. Okay, so P series. Okay, so the P series test looks something like this, and let me just get out my notes from earlier. Yeah. Yeah, you guys have got quite the hats. This is awesome. I'm so glad that you guys have your cameras on. You guys are the best. Yeah, what's going on over there? Oh, this is... Nice. That's awesome. So you stream, do most of you guys stream? Is that like a common thing amongst you guys, or is it just you? Yeah. Nice. Nice. What games do you guys stream? Oh, so everything. Okay, wow. Cool. So yeah, you guys have great setups. You got the microphone and everything. Cool. Okay, so I'm getting a little distracted here. Okay, P series test. P series test. Let's talk about the P series test. Okay, so P series test is another, convergence or divergence. So this is asking, do we have convergence? So this is another convergence test. So this one is not quite as convoluted as the alternating series test. So let's do the convergence test for this, or the P series test. So if we have a series that looks something like this, we're going from the sum of n equals 1 to infinity of 1 over n to the p, and my phone is still hearing Siri every 2 seconds. Really annoying. Okay, so if I have something like this, so this could be, and here p is a constant. P is constant. So where p is constant. So for example, we could have something like this, like 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared, right? Plus blah, 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 which would eventually actually look something like this. 1 plus 1 over 4 plus 1 over 9 plus 1 over 16 plus 1 over 25. Okay? So if we have this, then we converge. I should say this converges if and only if p is greater than 1. Okay? So what I mean by if and only if, so this is another one of those sort of logic things, like an if-then statement. So this means that the converse is true. Okay, so if we wanted to sort of deconstruct this sentence, this means that if p is greater than 1, if p is greater than 1, then we converge. If p is not greater than 1, or in other words, if p is less than or equal to 1, then we diverge. Okay? So if and only if statements are the kind of statements that most people think of when they think of an if-then statement, right? This is like these two things go hand in hand. So this p series converging is equivalent to p being greater than 1. If p is greater than 1, we converge. If p is not greater than 1, we diverge. Okay, so it's a very strong test. But the thing about it is that, you know, like the catch, what's the catch? Like, why can't we just use this all the time? Well, because not all series look like this. So not all series look like this. Hopefully, I mean, the idea is that hopefully we can sort of manipulate the series until we get something that looks like a p series. So this is what we would call a p series, right? This is our p series. So yeah, if p is greater than 1, then we converge. If p is not greater than 1, we diverge. So that's our p series test. And the last one that we have, okay, I'm going to give myself a check mark for that. So we've done the p series test. Finally, the integral test. Okay, sounds a little scary, the integral test, and in some ways it can be a little scary. Integral test. Okay, so if we're given the sum n equals 1 to infinity of an, okay, so it's a very strong test, but it can take a lot of work. Okay, so if we're given the sum from n equals 1 to infinity of an, what we can do is we can set f of n to be equal to a sub n. So basically, i.e., take our term as a function. And I don't like that wording. Let's say consider. So consider our term as a function. So and that our function is going to be in terms of n. Okay. So we're thinking of our you know like what you could call like as the summand, like the thing that's changing inside, like from term to term. Take that as a function, and then if the integral from 1 to infinity, so this is a improper integral, if this f of x, and we're going to change the variable to x, if you wanted to, you could keep it in terms of n, like, but it kind of looks a little bit weird to say dn, so we usually just turn that variable from n into an x, but it really doesn't matter what the variable is, as long as you're integrating with respect to that variable. So if the integral from 1 to infinity of f of x dx converges, then our series converges. N equals 1 to infinity, an converges. And in fact, this is an if and only if statement. So I'll just write it the long way, and I'll say if the integral from 1 to infinity of f of x dx diverges, then this diverges as well. An diverges. Okay. So these are oh, we got another streamer. All right. Hey, buddy. Okay, great. This is awesome. We should do this more often. Okay, so that's the integral test. So basically, all the integrals test is saying is say like, well, I mean, an infinite sum is pretty much just like an integral, right? I mean, you can kind of think of like if you looked at the graph of the function, right? So let's say that like in blue here, as like my legend, I'm going to say that this is our sum from n equals 1 to infinity of an. So basically, like let's say that this is going to be our sum. Like it's almost as if we're going backwards from a what am I trying to say? It's like we're going back. Like remember when we started off with a function and we turned it into a Riemann sum? we're kind of going backwards from that. So let's say that like this is what the actual sum that we're given is. It looks something like this. And then this is going to be like the integral from 1 to infinity of f of n. I should say f of x dx. Okay? So then basically we're just saying, okay, well, this is like our function here. So you can see that these two things have a lot in common with each other, right? They're not necessarily going to be equal, right? It's not like these are necessarily equal, but they're going to be close enough that if one of them converges, then the other one has to converge too. If one of them diverges, then the other diverges as well. So that's the integral test. So basically turning your sum into an integral and testing for convergence there. So that's another test. So the whole idea of this chapter is just learning about all these different tests so that we can determine whether or not an infinite series converges. Okay? Yeah. We did the ratio test yesterday? Yeah. It's a good question. Yeah. So just to sort of consolidate your question, if I understand correctly, what you're asking is like how do these correspond with the radius of convergence, right? So the ratio test, this is great for the radius of convergence, right? This is that's the gold standard for finding the radius of convergence. When it comes to the endpoints, however, this is where we're going to be using the nth term test, the p-series test, and the integral test. Okay, so the tests that I just showed you, especially the p-series test and the integral test, we're going to be using those with respect to the endpoints. Okay, so like yesterday we looked at an example. Which example was it? I don't think that we. Oh yeah, and here's I said we talk about edge cases tomorrow. Right here. So what we did yesterday is we looked at this one example, and we used the ratio test to see what the radius of convergence was. But the radius of convergence doesn't tell you about the endpoints, right? It doesn't tell you if the endpoints lead to convergence or not, right? It just tells you what's going on in the middle. But the endpoints we can use either the nth term test, the p-series test, or the integral test to test for convergence at those endpoints. So yeah, I hope that answers your question. So it looks like we're a little bit out of time. I'm gonna make the exit slip fairly straightforward today. So the exit slip, this one is not in the back of the book, unfortunately. I'm gonna ask what are, so exit slip. Let me zoom in here. We don't need all that. Okay, so what are the tests we know so far? Okay, just list them. Well, we've got the ratio test, we've got the nth term test, we've got the p-series test, right? Just write them down. They don't have to be in any particular order. Those aren't tests, those are types of series. Yeah. Like I could scroll up and I'd show you the answer, right? Yeah. I mean, you either wrote it down, or you could refer to YouTube, or you could look at the book. I think, what was it, one of these pages? Page 510. Great page, like I said. So that's your exit slip for today. Try not to keep it. I'm trying to keep it fairly simple. Like I said, the exit slip isn't intended to be like this super stressful thing. I just want to see who's showing up, who's paying attention to what we're doing and that sort of thing. So yeah. Oh, and look, we have a visitor. Say hi, Kima. Hey, buddy. Okay, I'm gonna go, and I will talk to you guys tomorrow. So hopefully tomorrow we'll get our hands a little more dirty. I just kind of wanted to consolidate this because I don't know, but like this is the first time I've been using this textbook, obviously, to cover this material, and it just seemed a little scattered to me. So I kind of just wanted to sort of consolidate everything. Tomorrow we'll go over some examples and get our hands a little more dirty, and yeah. Anyway, I'll talk to you guys tomorrow. Really nice to see your faces, I have to say. Just gonna be honest with you, it's been a rough week. I've had a really tough week, and it's just nice to see some faces and hear your banter, and you guys are funny, and it's great to have my students put a smile on my face. So thank you very much. Really means a lot. Okay, bye bye. Yeah.